This split-screen graph tracks two diverging realities in the artificial intelligence sector. On the left, we see the highly publicized drop in the unit cost of AI inference. Over the last few years, the nominal price to process 1 million tokens has collapsed. On the right side, we see the exact opposite trend in enterprise AI deployment. Total compute budgets for practical automation are escalating exponentially. Macroeconomic forecasts predict that cheap unit compute will lead directly to ubiquitous, low-cost displacement of cognitive labor. Yet the firms actually building these applications are facing massive compounding costs. Economist Dwayne Woods outlines the mathematical reason for this discrepancy. His research argues that current economic models miscalculate the structural scaling costs of artificial intelligence. We have to resolve this accounting error. If our scaling metrics are flawed, the macroeconomic forecasts predicting the rapid automation of white-collar work are based on a mathematical illusion. The standard macroeconomic model relies on a simple assumption. As the cost of compute falls, the cost of generating automated cognitive output falls proportionally. Leading automation economists regularly use this framework, projecting the historical trends of physical manufacturing directly onto AI. That logic comes from the era of mechanical automation. An assembly line operates on a monotonic mapping paradigm. A specific input maps perfectly to a specific output in a single pass. Make the machine run cheaper, and the product becomes cheaper. Applying that one-shot mapping framework to modern agentic AI is a category error. To calculate the true economic trajectory of artificial intelligence, we have to discard mechanical models. We have to treat AI production as a process of sequential search. The mapping paradigm applies to basic AI tasks, like direct translation. The prompt goes in, generating an output in a single pass. Token consumption is strictly bounded, scaling linearly with the text length. Agentic AI operates entirely differently, using a search paradigm. The final output is the terminal state of a complex trajectory through a massive solution space. The agent runs an operational loop. It proposes a solution, evaluates that solution against constraints, revises the approach if it fails, and repeats the cycle. The economic cost of this task is not a single inference call. It is the expected total number of iterations multiplied by the tokens consumed per iteration. Verification steps and retries compound that cost heavily. When an agent fails, the informational value gained is often far less than the massive compute spent generating it. Under the SETch paradigm, output length is completely irrelevant to the compute budget. A task's true cost is dictated by its expected search depth. This chart models that expected depth. The x-axis tracks the complexity index. The y-axis tracks expected tokens per task. As complexity rises, the likelihood that any single proposal will succeed drops exponentially. Because expected iterations are the inverse of success probability, token demand curves aggressively upward. It is strictly convex. A routine code function sits at a complexity of 1, costing roughly 4,400 tokens. Move to a non-routine multi-component task, and the cost jumps to 109,000 tokens. Push to a frontier integration task, and expected cost explodes to nearly 6 million tokens, 1,340 times more compute than the routine task. The final 10% of a hard cognitive task requires exponentially more compute than the first 90%. Small drops in unit token prices do not meaningfully offset the compounding search cost of production at this frontier. This dynamic mirrors a classic macroeconomic puzzle known as the index number problem. Theorists like George Stigler studied how changes in market composition alter real costs. In the AI sector, nominal deflation is real. The price per individual token drops steadily every quarter, but the overall economic basket of attempted tasks is shifting. As AI capabilities improve, firms direct models toward deep, complex engineering problems. This pushes the economy's AI workload deep into the exponentially expensive region. This creates token inflation. The token count required to complete a representative economic task inflates much faster than the price of the token drops. It is identical to a poorly weighted price index, where tracking nominal shelf prices gives a false sense of cheapness while total grocery bills rise. Measuring headline AI productivities strictly against nominal compute costs creates an economic illusion. It masks the prohibitive, compounding real costs at the frontier of development. When we scale this mathematics from a single task to economy-wide labor substitution, we hit a hard aggregate ceiling. This equation defines the feasibility of replacing human labor. It proves aggregate compute required for substitution grows exponentially. It dictates a strict efficiency race. Hardware capacity growth must outpace complexity expansion, multiplied by search difficulty. Hardware capacity growth is physically capped. It is constrained by semiconductor fabrication limits, finite energy grids, and the raw speed of data center capital formation. The right side of the equation, complexity expansion, is entirely endogenous. The mere promise of better AI pushes firms to chase harder problems, which tightly constrains their own feasibility in real time. Broad AI substitution is an ongoing race where algorithmic waste reduction must continually outrun the expansion of human ambition. Inelastic hardware capacity is currently colliding with massive token variance. Complex tasks demand so much compute that platforms are forced to heavily ration their resources. Systems solve this continuous knapsack problem by establishing a shadow price. The allocation algorithm systematically rejects and disadvantages high-complexity, token-heavy tasks to keep the system running. This convex demand curve breaks uniform, flat-rate SaaS pricing. A handful of heavy users running complex agentic loops generate unrecoverable compute costs that a flat fee cannot cover. We are watching the enterprise software industry respond to this math in real time, moving away from flat seat licenses and enforcing strict metered token pricing. We can apply this exact framework to the labor market. Tasks with structured, objective checks will face rapid displacement. Tasks with ambiguous verification protect human labor. There is a deep asymmetry at the complexity frontier. AI can generate candidate solutions cheaply, but autonomous verification in a complex domain, like legal strategy or high-level architecture, incurs the exponential token tax. The market response is a hybrid equilibrium. AI operates as a low-cost generator and intermediate searcher. Human experts are retained for final verification, specifically to bypass the massive compute tax of automated evaluation. AI will not achieve total, frictionless substitution of cognitive labor. Its economic trajectory is a hybrid restructuring, bounded by the unyielding mathematics of search complexity.